Friends, in this video, we will understand the basic concept of the load equalization and its different types of parameters which will be the effect on the load equalization characteristics. So, first of all, we can understand the basic concepts of the load equalization. So, in some drive applications, the load torque get fluctuates widely within a short intervals of time. So, basically, we have the basic fundamental concept, that is the dynamics of a electrical drive. So, in which we are using the motor load combination. This will be your motor, this will be your load. So this motor will driving these loads, so this is called as the motor, this is called as load. Such kind of torque of this motor is called as motor torque. This will be the angular velocity, and this will be the load torque, TL. Okay, so guys, what will be the concept of the load equalization? So in some of the application in electrical drive, the load torque gate fluctuates widely within a short interval of time. Means the value of this load torque will fluctuates due to the short interval of time because of some of the parameters of electrical drive may be disturbed. So the load torque's value will be fluctuation. So such kind of operation is basically available at the different types of application. So the first type of application that is called in pressing machine. So as we have in a pressing machine, if we are using some of the motor, for example, we are using some of the induction motor for your pressing mill, then what will happen at the pressing operation? We want the load torque of that pressing operation. That time the load torque value fluctuates, means the value of the load torque gets fluctuates. So that time we will require some of the mechanism, and that mechanism we will discuss later on. Okay, so that will be the first example. Then second type of example, that is called as electrical hammer. So in electrical hammer, obviously the value of such kind of load torque will be fluctuates. Then the next type of the example, that is called as steel rolling mill. So in again steel rolling mill, we are using, that is the load torques, that will be the value of the load torques may be fluctuates. Okay, the next example is called as reciprocating pumps. Then the next example is called as the blooming mill. So these are the some of the examples of your day-to-day life in a this industry where we can using the load torque, that will be the fluctuates. Okay, so due to what will happen when the load torque fluctuate, so obviously if the load torques will fluctuate, then the motor torque will also changes. Okay, so the motor torque, because this motor torque and load torque are connected to each other, if the value of the load torque will change, so obviously the value of the motor torque will change, that will affects. So obviously what will happen, this motor torque will draw the pulsed current from the supply, and due to the pulsed current supply, the voltage fluctuation will occur. So that will be the effect of the load torque fluctuation. So this will be the first thing that we want to reduce, and the second thing is that due to that particular thing, the stability of your electrical drive, means the stability of the motor load combination will be affect. So the reduce in the value of the stability of motor drive system. So that will be the second thing that will happen when the load torque fluctuates. Okay, so this problem of the voltage fluctuation and the problem of the reduced stability will be overcome by using a load equalization technique. Then next question will be coming into mind, what do we mean by the load equalization? So basically in load equalization, the load torque gate fluctuates. Due to the fluctuation of load torque, obviously the voltage fluctuation is there and the stability of electrical drive is reduced. So in load equalization, what we are doing, we are connecting some of the flywheel at the motor load combination shaft. So due to that, the load fluctuation will get reduced, and such kind of process is called as the load equalization. So friends, we will understand the concept of the load fluctuation. That is, load equalization is the process of smoothing the fluctuating load by mounting a flywheel on the motor shaft in non-reversible time. Means in the load equalization technique, we are mounting a flywheel on the motor shaft. Means we are using the flywheel. This will be the very important concept, that we are using flywheel on the motor shaft, and due to that particular flywheel, the fluctuating of load torque will get reduced. And if the fluctuating of load torque will get reduced, then obviously your voltage fluctuation will be reduced, and obviously the stability of your electrical drive will be the improved. So such kind of technique is called as the load equalization, or such kind of process is called as the load equalization of your electrical drive. So basically the very important concept while we are connecting flywheel, so obviously we want to find out what will be the J. That is, the J means the polar moment of inertia of your electrical drive. So we want to calculate the value of the J. So the value of the J will be in concern with your electrical drive system is very important concept. So this will be treated as on the priority of your electrical drive. So the moment of inertia flywheel required for the load equalization can be calculated. So we want to find out the value of the loads connecting flywheel, that is a motor load combination connecting flywheel, for the concept of the basic fundamental thing, and that the basic fundamental thing is called as the mounting of the flywheel on your motor shaft. So the mounting of your flywheel on the motor shaft, that will create some of the very important thing in your electrical drive, and that will be the important thing is called as the method of the load equalization. And in load equalization we want to find out obviously the value of the moment of inertia of that particular flywheel. So the value of the moment of inertia of that particular flywheel is basically treated as the dropping speed torque characteristics. Then we want to understand. So the dropping motor speed torque curve, variation of motor and load torque, and speed of the periodic loads are as shown. So in figure we are having, that is the torque speed characteristics. This will be your torque, this will be your speed. So in torque speed characteristics, what will happen, we want to first of all draw value of the torque, the value of the speed. Okay, so the torque speed characteristics is basically dropping characteristics, which will be shown by A and C. Okay, so in that particular curve we are having the value of the omega mo. This is called as no load speed of your drive. Then second, it is called as omega mr. It is the rated value of speed. Then next term, that is called as tr. Tr is called as rated torque of your motor, and tmax is called as the maximum torque of your motor. Okay, so these are the very important parameter in concern with the dropping speed torque of your electrical drive. So we can find out the value of the J, that is J, which is called as the polar moment of inertia of a flywheel, because in a load equalization we are connecting one flywheel on the motor shaft to stabilize the basically load torques. So that will be the very important concept. So we can start to derive such equation. So first step is to, we are now assuming the linear motor speed torque curve. That will be the again linear motor speed torque curve, in which we are having the different values of speed and torque. So the first value is the omega m 0, or it will be called as the omega IMO. It is the no load speed. Omega MR, it is the rated speed. It will be the TR, it is a rated torque. Tmax is the maximum torque. Okay, so basically the dropping curve drawn as the line which is called as AC, which will be passing through the line that is called as A to C, the line that is called as A to C, passing through various points, passing through the various points. So the first point is called as, that is 0 to omega mo, and the second point is called as tr to omega mr. So this will be the point. So from the basic mathematics, the line equation passing through that particular line, we will getting what will be, we are getting the x1 y1 and x2 y2. Suppose we are considering this point that is called as x1, and we are considering this point as a x1, this will be the y1. Okay, so this will be the y1, and this will be the x2, and this will be the y2. So we are getting the line equation, that is y minus y1 is equal to, in bracket, y2 minus y1 divided by x2 minus x1 into x minus x1. So from figure we are getting the equation, that is omega m minus omega mo is equal to, in bracket, the value of the omega mr minus omega mo divided by tr minus 0, and in bracket t minus 0. So from that particular equation we are getting the value of the omega m, that is the instantaneous value of the speed, that is equal to omega m0 or omega mo, it is called as no load speed, minus omega mo, it is again no load speed minus the rated value of speed divided by the rated torque into the motor torque. Okay, so this will be called it as the equation number first, and that first equation will be getting from that particular figure, and that figure is called as the simple line passing through a various 2 points, and these 2 points are treated as x1 y1 and x2 y2. Okay, so this will be the fundamental thing. So after the equation number first, so from equation number first, the basic slow response due to the large inertia, equation 1 is basically differentiating and multiplying both sides by the j, and that j is called as the polar moment of inertia. So now we want to multiply and differentiating the equation number first. So now we are multiplying with the help of the equation, that is j into d omega m by dt is equal to minus j into omega m o minus the value of the rated speed divided by the rated torque into dt by dt. Okay, so in equation number 2 we are just differentiating and multiplying both sides by j. Okay, so now we are getting very important term, and that term is called as the minus tau m. Okay, this will be called as minus tau m into dt by dt, that is the motor torque with respect to the time. Okay, so that will be the value, that is j into d omega m by dt. So in that particular equation we will getting the value of the minus tau m, and this is called as minus tau m is equal to basically the value of, that is j into omega mo, that is the no load speed, minus omega mr, that is called as the rated speed divided by the rated torque. So this will be called as the equation number 3, and equation number 3 is called as the value of the tau. And what do you mean by the term tau m is defined as the mechanical time constant of your motor. So this is called as the mechanical time constant of your motor. Basically, what do you mean by the mechanical time constant of your motor? So it is the time required for the motor speed to change speed from the no load to the rated speed when the motor torque is maintained at a rated value of tr. So what do you mean by the mechanical time constant? So that is called as the value or the time required for the motor speed change, that is motor changes from the no load speed to the rated speed value when motor torque is maintained at the rated torque. So this is called as the value of the tau m. Okay, so this will be the equation number 4. Now we are moving towards the equation number 5. So for the finding out the value of the equation number 5, we want to grade the fundamental torque equation and the equation number 3. So we are having the value of the fundamental torque equation, that is T is equal to TL plus J into d omega m by dt. So what will be the value of the J? The value of the J is called as the polar moment of inertia. The value of the T, that is called as motor torque, that is the Tm. The TL is called as the load torque, and d omega m by dt is the rate of change of the angular velocity with respect to time. This is called as the fundamental torque equation, and this will be the equation number 3. So this will be the equation number 3 from which we can get the value of the tau, that is motor time constant, that is J d omega m by dt is equal to minus tau dt by, that is the rate of change of the torque with respect to that particular time, that is a motor time with respect to time. So now we can getting the equation number 5. So the equation number 5, that is tau into dt by dt, that is the rated or the value of the motor torque with respect to the time, plus t, that is the t is called as a motor torque, is equal to load torque, that is called as TL. So this will be treated as an equation number 5 for your derivation. Okay, so now we can move towards the next equation. So for the understanding of the next equation, we want to understand a very simple concept of the load equalization. Consider a periodic load curve, a cycle of which consists of one high load period with torque TLH. So first of all, we can understand, guys, we are having the load characteristics, that is a load torque characteristics with respect to time, that is T. So this will be the characteristics of the torque with respect to time. So we are basically having the two types of torque. First type of torque is TLH, that is called as the high load torque. It is TLH, which will be shown by here, that is TLH. So this is called as the high load torque. And second type of torque, which is called as TLL, it is the light load torque. This light load torque will be shown by here, that is TLL, TLL. So this is the light load torque. The timing for the high load torque, it will be duration, that the duration of the high load torque, which will be shown by here. So that the duration of the high load torque means that the duration, this will be the duration of the high load torque, and this duration is called as TH, that is the timing for the high load torque, or the timing for the high load torque. This is called as TH. And second term, that is the TL. What do you mean by the TL? It is the timing for the light load torque. So this will be the timing for your light load torque. This will be the timing for your light load torque. And in between, we are having the value of the torque, that is T minimum value to the T maximum value. This is called as T max and T minimum. So friends, in that particular characteristics, we are getting the value of the torque, that is from T minimum to T max, again is from your T max to T minimum, again is for your T minimum to T max, again it will be for your T max to T minimum. So this process will be the continue for your particular application. And concern with that, we are getting the value of the reduction in speed, that is called as the angular velocity. So this will be the value or the curve of the omega m. So this will be very important periodic load curve, in which we are having the basic concept, because in day-to-day life we are using the different types of application. For example, the press machine. So in press machine, the value of the torque with respect to time we are getting. Some of the time the load torque is very high. At some time the load torque will be very less. Again it will be high. Again it will be less. Again it will be low, again it will be high. So this is called as the load torque, this is called as a load torque, but this will be the for your high load torque. That's why we call it as TLL. LH, that is called as TLH means high load torque, and this will be the load torque for TLL. TLL means light load torque. The timing for the high load torque, it is called as TH, and the light load torque, this is called as TL. So that will be the basic fundamental concept, that is called as periodic load curve cycle, for which consists of the one value of the high load torque, and the second, this is called as the value of the light load torque. Okay, so I think everyone has got the concept of this curve. So we will move towards the next bit, that is very important bit, is concerned with basically the derivation or the finding out the value of the J, that is polar moment of inertia. That will be the polar moment of inertia of your flywheel, that the flywheel we are connecting for the load equalization of your electrical drive. So for the value of the high load period, when the timing is greater than 0 but less than the high load timing, so the solution of the equation number 5 becomes, so this will be the equation number 5, that is T is equal to TLH in bracket 1 minus e raised to minus T divided by the tau m, that is the tau m is called as a motor constant, plus T minimum e raised to minus T divided by the tau m. So this is the equation number 5, and from that particular equation number 5 we are getting the value of the equation number 6. And what will be the value of the equation number 6? That is the T means the timing is equal to greater than 0 and less than the high load timing. So this is called as equation number 6. When T minimum is a motor torque at T is equal to 0, which is also the instant when the value of the heavy load, that is TLH, is applied. If motor torque at the end of the heavy load period, that is called as the ID into Tmax, then from equation number 6, then we are changing the equation number 6 from a basic fundamental thing, and we will get one of the important equation number 7, and that the equation number 7 is called as Tmax is equal to TLH, that is the load torque for the high load, in bracket 1 minus e raised to minus Th divided by tau m, bracket complete, plus T minimum, that is e raised to minus Th divided by tau m. So this will be the equation number 7 for your sake of understanding. Now we are moving towards the next equation, that is the equation we are getting from the fundamental thing from the equation number 5. So the solution of the equation number 5 for the light load period, that is the light load period, is called as the value of the T, that will be the greater than Th, then the but less than the addition of the high load torque, that is the timing for the high load torque and the timing for the light load torque, with the initial motor torque equals to the Tmax. So Tmax is the value of the maximum torque at that particular position. So we are getting the basic equation number 5. This is called as equation number 5, in which we are getting the T is equal to TLL in bracket 1 minus e to the power of the T dash, where T dash is called as a timing, divided by tau m, bracket complete, plus Tmax, that is e raised to minus T dash divided by tau m. So this will be the equation number 5, and from that particular equation number 5 we are getting the value of the T dash. And what will be the value of the T dash? So the value of the T dash is obviously greater than 0, but the value of T dash is obviously less than the TL, where TL is called as the load torque time. Okay, so this will be called as equation number 8. So where we can get the value of the T dash, and the value of the T dash is called as T, that is total time minus the timing required for the high load. So this will be called as the equation number 9. So from that particular equation, now we are getting the next equation, and that the next equation, when the operating in a steady state motor torque at the end of the cycle will be same as the beginning of the cycle, so that the beginning of the cycle, which is treated as the hence, that is the T dash is equal to TL, that is a light load, and T is equal to T minimum. So obviously substituting in equation number 8, the value of t dash is equal to greater than 0 but less than the TL. That will gives one of the important equation, that the one of the important equation is called as T minimum is equal to TLL in bracket 1 minus G to the power TL divided by the tau plus T max, that is e to the power minus TL divided by the tau. So this is treated as in the equation number 10, and basically this equation number 10 is getting from the equation number 8, that we are substituting the value in the equation number 8, that is the T dash is equal to TL and T is equal to T minimum. So we are getting the value of the equation number 10. So after getting the value of the equation number 10, we are getting the basic fundamental thing from the equation number 7. So from equation number 7, we are getting the value of the T max, that is TLH in bracket 1 minus e to the power minus TH divided by the tau plus T minimum, that is e to the power of minus TH by the tau. So this will be the equation number 7. So from that particular equation number 7, we will get the value of the tau, that is a motor time constant, that is tau is equal to TH, that is the time required for the high load, divided by log to the base E in bracket TLH minus T minimum divided by TLH minus T maximum. So this will be treated as an equation number 11, and from that particular equation we are getting the value of the motor time constant, that is tau. Okay, so for the next step, from equation number 4, that is the equation number 4 is what? It is the tau is equal to J into omega mo, that is the no load speed, minus the omega mr, that is the rated speed, divided by the rated torque, this is called as TR. So from equation number 11, that is equation number 11 is what? That is tau is equal to TH divided by log to the base E in bracket TLH minus T minimum divided by TLH minus T max, bracket complete. So from that particular equation number 4 and for equation number 11, that is from equation number this and this, we are getting one of the important equation of J, that is J is called as the polar moment of inertia of flywheel is equal to TR, that is rotor torque, divided by omega m0 or omega mo, that is called as the no load speed, minus omega mr is called as the rated speed in bracket TH, it is the timing for the high load torque, divided by log to the base E in bracket TLH minus T minimum divided by TLH, that is the load torque for the high applications, minus T max, whole bracket complete. This will be treated as an equation number 12. Okay, so from that particular equation we are getting the next equation, that is the equation number getting from the equation number 10. So what will be the equation number 10? So we are having the value of the equation number 10, that is T minimum, that is the timing required for minimum, is equal to TLL, that is time required for the light load condition in bracket 1 minus e to the power minus TL divided by tau, that is a motor time constant, plus T max e raised to the minus TL divided by the tau. So this will be the equation number 10. So from that equation number 10, we are getting the value of the tau is equal to TL, that is the timing for light load, divided by log to the base E in bracket T max minus TLL, that is the torque for the light load, divided by T minimum minus TLL, that is a basically timing required for the light load characteristics. So this will be the equation number 13. Okay, so from the equation number 13, now we are moving towards the very important equation, that is the final equation for your J, that is polar moment of inertia. So that the final equation we are getting from the equation number 4. What will be the equation number 4? This is the value of the motor time constant, that is tau is equal to J into the value of the omega mo, that is the no load speed, minus the value of the rated value of your speed divided by the rated value of torque. And the equation number 13 that we had already derived earlier. So tau is equal to TL divided by log to the base E in bracket T max minus TLL divided by the T minimum minus TLL. So it will give you, we can get very important equation in concern with J, that is polar moment of inertia of your flywheel, is equal to TR, that is called as a rated torque, divided by the omega mo, that is no load speed, minus omega mr, it is the rated value of your speed in bracket TL, that is the timing for light load torque, to the log to the base E in bracket T max minus TLL divided by T minimum minus TL. So this is called as a equation number 14. So basically this will be the very important equation as concerned with the polar moment of inertia of your flywheel. Then next we are getting the value of the moment of inertia from equation number 12 and from equation number 14. So we are getting the value of the, that is moment of inertia of your flywheel. This is called as equation number 12. So in equation number 12 we are getting the value of J, that is J is equal to rated motor torque divided by omega mo, that is no load speed, minus the value of the rated speed in bracket TH, it is the timing for the high load torque, divided by log to the base E T TH minus T minimum divided by T TH minus T maximum. This will be the equation number 10, 12, from which we can getting the value of J, or equation number 14. Equation number 14, again this equation will give you the value of J. So J is equal to what? TR divided by omega M0 or omega MO, that is no load speed, minus omega MR, this is the rated value of speed, TL, that is for your light load, log to the base E, that is T max minus TLL divided by T minimum minus TLL. So from that particular equation we are getting the value of the J for your light load, and this is for your high load. Okay, so from that particular equation we are getting the value of J. So what do you mean by the J? J is called as polar moment of inertia of flywheel, is equal to W into R square. So the value of J, the value of J in terms of kg meter square. So what do you mean by the W? Where W is called as the weight of the flywheel and the R is called as the radius in terms of meter. So that's why the unit of J, that is polar moment of inertia, is called as omega into R square, where W is weight and R is the radius. So that's why the unit is kg per or kg meter square of your J polar moment of inertia. So friends, in this way we have studied what do you mean by the load equalization characteristics, and by the using or by the mounting of the flywheel we can reduce the fluctuating, that is called as the fluctuating load torque. So due to that the voltage value is improved and the stability of your electrical drive will be improved. So this will be the concept in concern with the load equalization of your DC, or the call it as the electrical drive. So thank you.